Alright, the aim of this video will be to establish a way to change the base of a logarithm to any number of our choice, most commonly e, which is very useful for both evaluating these logs on our calculator and also doing other important things with them later, like calculus. Okay, so let's go over again what the logarithm does. Suppose we take log base 10 of 1000 here. How we've previously thought about this is by making 10 a base number, 1000 is our target number, and then we ask for what sort of power we need to hit the 10 with in order to arrive at the number 1000. Okay, and in this case, it should clearly be 3. Another way to think about this is that in the world of multiplication, and be very careful with this, it's only in that world of multiplication, okay, 1000 is made up of 3 copies of 10. And that sort of perspective will be quite helpful later, so file that away, okay, and we'll do the same thing again with a different one. So say if we take log base 1000 this time, of a million here. We could just say that a million is made up of 2 copies of 1000 multiplied together, so that log would equal 2. Okay, now you might be able to see where we're going with this. Let's start again with the biggest number from before, so 1 million. Then we've seen that he breaks into 1000 times 1000, so that means a million is made of 2 copies of 1000 multiplied together. So we write log base 1000 of a million equals 2. But now each of these copies of 1000 is actually made of 3 copies of 10, and all of them are being multiplied together. And because of that, we would write log base 10 of 1000 equals 3. But if we now kind of skip the middleman, so to speak, we find that a million is actually just made of 6 copies of 10. That is, we can go straight from the top to the bottom by saying log base 10 of a million equals 6. Now that's something you could hopefully have seen already without the middle guy, but the takeaway from all this is this relationship between the 3 logs that are in front of us right now. Okay, and they're clearly linked by multiplication. That is, well, 6 is equal to 2 times 3. And why should it always be like this? Well, because the starting number, the million, right, was made of 2 copies of 1000, and each of those thousands were made from 3 copies of 10. So in total, the million is made from 6 copies of 10, and it's this pattern, this sort of multiplying relationship that you want to take away from all this. Okay, so let's generalize. What we've just seen can be written in general as log base x of y times log base a of x equals log base a of y. Okay, we've just written what we've just done in algebra, in symbols. Let me show you again and go through it again, starting from the left, because it looks a lot more confusing now that it's in symbol form. If we pretend that y is equal to a bunch of x's multiplied together, then log base x of y tells you how many of copies of x the number y is made of. Then presumably, each of these copies of x is made up of a bunch of a's multiplied together, and what log base a of x tells you is exactly how many of these there are, okay, for each copy of x. So by the time you've multiplied these 2 logs together, you've effectively counted how many copies of a the number y is made of, still in the world of multiplication, by the way, which is exactly what log base a of y on the right-hand side there is. In general, we often write this top equation, though, in fraction form, like this. Okay, and the reason is that this gives us a way to change the base, which was our goal from the beginning. Right, note that the log on the left has a base of x, okay, and both logs on the right have a base of some other number a. Right, and note that this number a is like our free choice, right? No matter what x and y are, right, that number a could have been chosen out of thin air. Okay, it doesn't matter what the a is because the same reasoning would still work. And in particular, that number a could be chosen to be a useful one, right? So either e or 10 or whatever, which are logs found on our calculator, and you'll be playing with that a lot today, right? And writing it like this is also a pretty nice visual sort of pattern. If we have some strange log with a random base, we can change to a familiar base by taking a fraction of logs where the target number goes on top and the base number goes on the bottom. Okay, so it's sort of visually kind of easy to remember as well, I guess. But of course, as with everything, the reason behind it is much more important. Okay, so let's finish by seeing one example of this in action. I started this whole topic with the equation 3 to the x equals 10, okay, which we could write the answer to sort of from day one as log base 3 of 10, but we could never quite work out what kind of decimal that would be exactly, okay? We knew it was between 2 and 3, but we didn't know how far, okay? But now we can change base. Okay, now I really like the number e, so I'll change to a base of e. To remind you also that that looks like ln on your calculator. Okay, so remember how we do this change of base is we form a fraction of logs. And see how on the right hand side, both those logs have had their base changed to e, and so I'm writing ln for both of those. Okay, then the target number 10 goes on top, the base number 3 goes on the bottom. We slam that into our calculator, and out comes 2.0959 blah blah blah. And that's the change of base in action. Okay? Now it's got some like actual proper nice uses in like calculus and stuff, because there we pretty much always want the base to be e, because as we've sort of seen previously, e works really well with calculus, but that's a story for another time. So thanks for watching, and I will see you around.